Let's kick off this session. So good morning once again, everybody, and thank you for taking the time to attend our session. My name is Mark Dennis. As Katrina's introduced me, I work for Systems and Network Training in the UK, and I have spent probably the larger part of my working professional life as a networking, data networking professional, which is going back quite a number of years now. LINX and Systems and Network Training have collaborated many times to bring these webinars, and we hope that this information transfer will be useful to you. The subject of this webinar, as has been introduced, is on route servers. Route servers, in particular, for example, as used with LINX in the London Internet Exchange. Over the last, let's say, 15 or more years, the use of internet exchange peer points to interconnect the internet network service providers has grown significantly. And route servers have become a prominent enabler of those network interconnections in the internet exchanges. So really, this webinar is designed to take a closer look at route servers and see how they function. So this is a 2-hour webinar. We'll be taking a break around about the 55-minute mark. Please do ask questions. There is a Q&A button for questions. We'll take those and we'll answer them when we come back from the break, and then there'll be another chance to ask questions just before the end of the session, just before we wrap up at 12. So who's in this webinar? Well, the presentation is mainly aimed at an audience who are interested in and involved in internet infrastructure operation. We will be talking to some technical degree. That's what my organization does. It teaches technology. And so we'll be talking about things like BGP, route servers, multi-lateral interconnections, and connections between BGP autonomous systems. If you don't know what those terms mean, please do stay. I will be explaining them as we go through. So really, this subject aims to help you to understand and illustrate the use of route servers, such as those used by LINX in the London Internet Exchange. So here's a set of objectives. Again, we're going to first start pretty high level, understand what route servers are and why we use them, how they're useful. We are going to just discuss some of the fundamentals of this thing I mentioned before, BGP, Border Gateway Protocol. It's a routing protocol, and we need to understand a little bit about that to see the significance of what route servers are doing and how they are so useful to us. We'll be looking in general at how a route server behaves. What are its functions? How does it do what it does? And how does it behave differently to a standard internet router that is using the BGP protocol? And then that'll take us up to the first half. In the second half, we'll be taking perhaps a closer look at the configuration and architecture of route servers, looking at things like being able to monitor their operation, and also to understand and demonstrate a little bit regarding the filtering that they use, and more on that as we go through what we mean by filtering. So that's the overall agenda, what we'll be covering today in this next 2 hours. So let's start with the basics, understanding what the role of route servers is. And in order to do that, we are going to discuss these three, or try and answer these three fundamental questions that you see on here, which is what is a LINX route server? Why are they important in the internet? and what role do they have in the world of internet routing and BGP peering? So if we look at the construction of the internet, there are thousands of internet service providers with hundreds or more interconnections between those service providers and other service providers across the internet. Together, they make up the internet with their interconnections. And the internet is not just about service providers and their routers, and that's what these symbols on here are all about. These are internet routers, these kind of hockey puck looking things, if you've not seen those before. The service providers themselves can range from small regional local corporations and can go up to being large national and international organizations covering, a multi-continental geography. They link together, but not only do service providers themselves link together to make up what we know as the internet, but also the internet is made up of the consumer giants, people like sort of Facebook, for example, and, Amazon, people like that. The cloud giants, which would also include, Amazon and Microsoft and Google, etc. Content giants like Netflix, content data network providers like Akamai and Limelight, and then large businesses as well, and obviously sometimes smaller businesses too. All those organizations have some sort of infrastructure that connects together via routers, and they register what we call an autonomous system. And we can see down here that as of 2021, there are now in excess of 100,000 autonomous systems interconnected up into the internet. So 100,000 different organizations are connecting their routing infrastructure into what we know as the internet. These connections, for example, as I'm sort of illustrating very simplistically here, we call peering. Okay, so peering is a description to describe the way that one organization's router connects to another organization's router. Whatever size those organizations, we call that peering. So smaller regional ISPs might have, internet service providers might have somewhere from a few dozen to a few hundred of these peer connections. And those connections could include both service providers with whom they exchange information, or customers whom they are connecting up to the internet. Larger international or national service providers may have significantly more connections than those dozens to hundreds. They could have thousands of interconnections. In the less developed countries, maybe because of infrastructure limitations, we tend to see fewer interconnections between service providers. So peering then, as I'm trying to illustrate on here, is a fundamental relationship between an organization's routers. It's something that you do as an internet router belonging to one given organization when you want to exchange routes with another organization. You peer with them. The peering is a communication session between those routers of the different organizations. And the point about doing this peering is that you want to pass on routing or networking information to allow the data packets, the communications between devices across the internet to flow. More specifically, BGP is the routing protocol that these routers are using, and that is what's used more correctly across the peering connections to pass routes between routers. So ISPs must use these BGP sessions to send and receive routes amongst themselves. Now, without route servers, if we want to provide direct connections between the routers of one organization and, dozens or maybe hundreds of other organizations, then the number of these peering sessions, using the BGP routing protocol is going to become a very large number. In fact, that's what this kind of, equation on the slide is trying to show us. So N here is the number of, for example, ISP routers that want to interconnect to build peering and share routes amongst other internet service providers. If this number N were 50, so 50 internet service providers want to interconnect amongst themselves, then they would have to set up 1,225 connections to enable that to take place, which is obviously a large number. It means a lot of configuration. It means a lot of load on their routers. It means a lot of complexity and, basically operational complexity and difficulty as far as the operational teams are concerned in those internet service providers. And the bigger that N number becomes, the larger that number of session grows, and it grows sort of fairly exponentially or as a square factor. So now we come to the context of what a route server is actually doing. So the London Internet Exchange, for example, as we're illustrating here, provides an interconnecting set of infrastructures, a high-speed backbone, if you like, that allows service providers to interconnect. I've drawn 5 service providers on here, and they each have an autonomous system number, one of those 100,000s that we talked about, and they interconnect via the switching infrastructure of the Internet Exchange, such as LINX provides. So, and this has become, a growing trend over the last number of years, so that now people like LINX have, hundreds of different service providers that interconnect via them. So what does a route server do here to perhaps reduce some of that burden that we mentioned before from the potential number of interconnections that we would need between these service providers? If there's just 5 like we see here, then the problem wouldn't be so large, should we say. But because we're talking about, hundreds of different service providers wanting to interconnect via these internet exchange points, then what route servers provide is a simplification of the interconnection infrastructure and a huge reduction in terms of those numbers of interconnections that we mentioned before. So instead of and service providers are still have the option to directly connect if they wish, and that's what this line is on here. There's a direct connection there. But what the route servers provide, which is shown by the dotted lines on here, is that instead of the service providers' routers having to directly connect with each other and have these huge numbers of connections, then the service provider router interconnects and peers with just the route server itself, which is provided by the Internet Exchange. So If there are 5 service providers interconnecting here in this exchange, and they all want to use the root server, then they each only have a single session to set up to the root server itself. So the root server will have 5 connections, and each service provider has just a single connection. If there were 50, then there would be a single connection from each of the 50 service providers into the root server, and the root server would have 50 connections back to each of the 50 service providers. The point here being that that single connection from the service provider router to the root server is an awful lot better than the 1,225 that we talked about if there were 50 service providers wanting to interconnect. Huge amount of simplification. However, what the root server is doing when it peers with those service providers, it is still passing on the routes that we talked about before in BGP among the different providers, among the different autonomous systems. But this time, all these autonomous systems need to do is announce their routes to the root server, and the route distribution will happen on their behalf by the root server. So that's fundamentally what a root server is doing. It's doing route distribution, and it means a great deal of simplification in terms of the configuration and operational aspects, because now the service provider just has to monitor one connection into the root server, maybe 2 if we're talking about redundant infrastructure, of course, and a great deal load reduction because each router does not have, hundreds or thousands of sessions in BGP. It just has a single one to the root server itself. If we take a look at, for example, the London Internet Exchange root servers, as we can see here, we can take a look and see the sort of scale of connectivity. I'm just actually going to jump over to the live web page that represents what I was looking at there on a slide. So this is a view of LINX's root servers, including the London root servers. So here we see a list of the root servers that LINX has. There are 4 in London, there are 2 in Manchester, 2 in Nairobi, 2 over in the States in Nova, a pair in Scotland, and a pair in Wales. And what we can see is that each of those root servers is connected up at just 1 gigabits per second of speed and has its own IP address. Perhaps more interestingly, if we click on just one of those root servers, which is the first one in the London Internet Exchange, we can then see the names of the providers that are connecting up through that service provider here. And you'll see some, very familiar names, for example, like Adobe on here. You'll see people like Akamai, who are these content providers, Apple, etc., etc. And if we go over to the left-hand side, you can see that this root server has 817 peers of its own, which would, if they were individually peering with each other, mean about 1/3 of a million BGP sessions, a huge number. So that number can be greatly reduced by the use of root servers. So that's fundamentally what root servers are and why they're useful to us. If we just go and have a quick look at BGP and try to understand a little bit about BGP as well, I think that will be useful to us because I do have a sort of a lab environment set up here where we're going to have a look and see how this peering takes place, what it looks like, and what it looks like with this BGP protocol. So let's put this into context. There are two types of routing protocol. Pro, it's a mechanism, it's an application, if you like, that lives on a router. A routing protocol is an application that lives on a router. The two types are first an interior, what we call an interior gateway protocol that runs within inside an organization, or what we call an autonomous system. And then we have an exterior gateway protocol that is a routing protocol that runs between autonomous systems. So just to define what an autonomous system is, an autonomous system is a group of routers owned and administered by a single organization. So if you like, an ISP or an enterprise will have an autonomous system with routers running inside it. They have their own routing structure inside, but when they want to link up to the internet, or they want to provide connectivity for their customers to other service providers, then they interlink using the BGP routing protocol. BGP runs between those routers. BGP is peering between those routers. They can either directly peer, as we said before, or these peerings can be via Internet Exchange and via route server, which is going to help us with scale and all that sort of stuff that we just talked about. So I have a demonstration environment here in which I hope to show you how these peerings work and how the route server functions to distribute routes, although we have a very simplified setup by using route servers. So here I've got what is representing 8 different customers or 8 different autonomous systems. Each of those has a single router on it. Each of the customers has a number. So an autonomous system has an autonomous system number, and I've numbered these 11 for AS11 all the way up to 18 for AS18. Those 8 routers are interconnected through what is representing the Internet Exchange switching infrastructure, which is what these devices here are doing. And then connected also to that infrastructure is the route server, which is running up here. The route server also has its own autonomous system, which is AS number 250, as you can see here. Now, how these devices are all connected, the route server and all these 8 routers here, is they're connected on a common network. And this is how it will be at an internet exchange such as LINX. Okay, this is my network number, not LINX's network number, but this is a common IP network 1099.99.0/24, which is used to connect up these service provider routers and the route server over here. And so every router has an address, as you can see here, on that network. Now, each of these routers is going to be advertising its address space. And the way I've done this is that there is a loopback interface on the router with an address, which is using the same sort of numbering as you can see in their AS number. So to keep it simple and keep it visible, for example, here, Autonomous System 11 is advertising the 11.11.11 address. And Autonomous System 18 is advertising the 18.18.18.18 address. And they are all peering only with the route server in Autonomous System 250. Okay, so that's the lab setup. If we go to the routers, I'm going to show you some router configuration here. Okay, this is a technical session, so I'm going to show you a little bit of technology. Don't have to get bogged down in it, but what this is showing you in a slide is, for example, router 11 in Autonomous System 11 and who he's peering with. and he's peering with just one neighbor, which is the 10.99.99.120 in autonomous system 250, which is the root server here. Okay, and just to show you this is not smoke and mirrors, I'll jump over to my my setup environment here. We'll go on to router 11 and do a show IP BGP summary. That's a summary of the BGP peerings we have, and we can see that we're just peering with the root server. So that's all you have to do to interconnect via an Internet Exchange root server when you want to interconnect or when you want to join the infrastructure that allows you to advertise your routes to other members of that Internet Exchange. We're going to see the routes in just a second, but for now, I'm just going to jump back into my slides and just give you a little bit more explanation of what BGP is. So BGP is the routing protocol that runs between different customer networks, or as we call them, different autonomous systems. Each customer network has its own autonomous system and its own address space, and BGP allows us to share that address space to enable routing to happen across the internet. An end customer doesn't necessarily have to use BGP if they've got a very simplified setup. So if they're a domestic customer or an SME and they're just connecting to one service provider, they could use a more simplified setup of static routes. But if you're a large organization and you're connected to several service providers at different POP points, then BGP is going to be the best way to connect yourself to the internet. When you connect using BGP, your router, so if I'm this service provider here in AS1 and I want to connect to service provider in AS2, I need to program my router to go and talk to the router of the other service provider. And he has to do the same in the other direction. So it's a purposeful connection between routers, which will enable that peering session. And once we have a peering session, we can then advertise routes to each other. So for example, here, if I am that router in AS11 in my lab setup, and I want to talk to the root server over here in the lab setup, I will go into my router and I will start the BGP process, which is what this line here is doing. I will state the BGP remote peer that I want to talk to. So I give it the IP address of the root server and the AS of the root server. And then I will advertise my network, or I will advertise the network that I want BGP to advertise for me. So if I'm the router in the 11 AS, I'll be advertising this 11.11.11.11 here. If I'm talking to a root server, as opposed to directly peering with another ISP's router, I also need to have this in my configuration. So when you're a member of an Internet Exchange and you're doing this multi-lateral public peering via root servers, you do have to modify your configuration slightly because in normal BGP operation, I would need to see the autonomous system of the router that I'm doing BGP peering with when that router is sending me updates. However, one of the changes that root servers perform is that when they advertise routes to their members that are connecting to them, they do not advertise their own AS. The root server will be in its own AS as discussed, but it won't advertise its AS. And we need this line in our router, for example, if you're using a Cisco type configuration, to allow your router to accept that situation. Once the routers are talking, what they do is they send messages to each other. They keep their peering alive with keep alives, and they send routing updates, and they send notifications to them, to each other. And if you were to use something like Wireshark on the link between your routers, you would see these BGP packets, for example, these keep alive packets, which are used to keep that peering alive. So once, if the peering's alive, then routes can be exchanged. So for example, here, if I were to look at Wireshark on this switch, which is connected to the root server up here, you can see some BGP keep alives in there. If I change my filter to just look at BGP, then you can see the BGP keep alives for the sessions between the 120 router and the 17 router, between the 120 router, which is the root server, and the 12, the 14, the 18, etc. Those routers are continually talking to each other to keep that session alive. So root server fundamentals then. Let's talk, we've seen we've seen what benefit they can provide. How are they actually functioning? In the second half of this presentation, after the break, we'll be looking in more detail at the actual configuration. But for now, I just want to provide some specifics about the way that a root server behaves, and how it might behave differently, for example, compared to like an ISP's or a business or an enterprise BGP router. Really, any router that's capable of BGP can be set up as a root server. But a root server behaves in a slightly different way to the way that a standard BGP peering router would behave. If you're an internet exchange, the internet exchanges in general don't use a bespoke, hardware-based platform like you might see from, the likes of Cisco, Juniper, etc. They tend to use a software-based distribution for running their root servers on. The root server software can run on, standard server type of hardware, and that hardware will have multiple interconnecting interfaces into the internet exchanges backbone switching infrastructure. The software that is running on those standard servers, in general, is an open source software distributed under, GNU public license. And the main three varieties are Bird, Quagga, and Open BGP. At LINX, they are using a combination of Bird and the Open BGP daemon. Software distribution of a routing daemon to operate on their root servers. In my demonstration environment, I'm using Bird, as I'll show you in more detail later on, and I'm using version 1.68 of Bird. There is a later version 2 something, and it may well be that that's what they're using in LINX, but for my intensive purposes of this presentation and my simple demonstration, I'm using version 1.68, just to let you know. So this is perhaps a slightly out of date slide now. Bird is still used, but in the context of the LINX Route servers, they have redundant pairs of route servers in each of their locations, and in many cases, one of them will be running Bird, and the other one will be running the open BGP Daemon. You can see here that in LINX, they use a common autonomous system, which is number 8714. So all of their route servers that are connected to all of their member peers in their internet exchanges, they're all connecting to the route servers that they have, which are on a common autonomous system here of 817. And that exists across all of these different locations that we saw before. So, the big picture with route servers and how they operate is that, you as an organization, or someone as an organization who wants to interconnect to many other organizations through an internet exchange. The benefit of the internet exchange is that it can provide you with local connections for very fast interconnections for very low latency internet communication with many other organizations locally in one of the internet exchange facilities. But you can do so simply and easily without having these thousands of BGP sessions by connecting or having a BGP session yourself with the route server that is provided by LINX in their internet exchange. So these addresses are just for illustration purposes only. There is a common network here of XYZ.0/24, and all of the ISP or cloud giants or whoever they are, they're all interconnecting from their autonomous systems with their routers through this infrastructure on a common network. And if they want to multi-lateral peer with these other organizations, they can have a single session with the route server to do so. So if this organization wants to advertise its routes, it's going to advertise its routes to the route server, and then the route server is going to take those routes and advertise them on to the other organizations that are connected to this infrastructure here. Let's look a little bit about, let's just take a little look at that process of route passing that we mentioned there. If we just take two members that are interconnected in this internet exchange infrastructure, let's say organization 18 here wants to advertise routes into this infrastructure. It's peering with the route server, and it wants to advertise its routes to the router in organization 17 down here. So it doesn't directly have a peering session with 17, and 17 doesn't have a peering session with 18, but they individually have a peering session with the route server. Now, in BGP, when you advertise your routes, you have to advertise them with your AS. So 18 here will have to advertise its autonomous system number 18. And when it's advertising routes, it's saying, come to me if you want to get access to those routes or to those networks that I'm advertising. So it takes those advertisements, those BGP routing updates, as they're called, and it advertises them over to the route server, and the route server passes them then on to 17. Normally, when a router, like we're seeing over here, passes on routes, it advertises its own autonomous system. So here that would mean advertising the 8714, and it advertises its own IP address as the place to get those routes. But a route server does not do this. Okay, what a route server does is it takes the route that's advertised by 18 over here, which is coming from, in this case, the .18 address and the AS18, and passes that on directly as is to organization 17 over here. So what organization 17 sees is this addressing coming from this address and coming from this autonomous system, and the same back in the other direction. So the route adverts are going to the route server, but they're seen as coming from the member itself as where they're who's advertising these routes. And what that means is, from the point of view of actual traffic flow, as in data packets, is this, that when you're advertising the packets here, the packets are going into this infrastructure and going through the interconnecting infrastructure, but directly between the organizations. And, you know, these speeds, these can be 10 gig, they can be 100 gig, they can be, you know, 400 gig, they can be very, very fast in terms of bandwidth, an awful lot of data going through the routers of the internet. We don't want that going through our route server because it would fall over. But because of the way we advertise routes in a route server, the packets are actually going through the very fast interconnection, peering interconnections in here, and the packets are traveling directly between our members. If we go into the routers themselves to see where the routes are being advertised from and how we see them. So if I go into router 11 here, we will see that the routes from so this is the local router 11's route. It's got a next hop, if you like, of where it comes from. It's got 0000 because it's its own route. And it also doesn't advertise to itself its own autonomous system number. But the routes coming from 12 to 18 in our demonstration setup, they're seen as coming from the address of those other 7 routers in AS's 12 to 18. And we can see that over here where we see where the routes come from. This is the address space from the individual other 7 ASs. Those routes are seen as coming from the router addresses of those devices, not from the route server, and they're seen as coming with the autonomous system being advertised of those routers as well. So I'm just going to jump over to the actual demonstration environment here. We can see our keep alives are still running. Let's go back to our setup here, which we can see. So just to remind you of our setup, we have these 8 autonomous systems. They're connected via this infrastructure. We have the root server over here on 120, 10.99.99.120, and each of these routers are on their individual address, 10.99.99.11 up to 10.99.99.18. And their ASs are 11 to 18. The AS of the root server is 250. So if we jump onto this router here, the router in AS11, for example, and take a look at, we've already seen that it's peering, as you can see here with the root server. And if we do issue this command to see its routes, as we just saw in the slide, we can see what we just saw. So it's not smoke and mirrors. We can see its local route that's coming from itself and the routes from the other 7 autonomous systems, just taking, for example, this one here coming from router 12 over here. We can see that that route 12.12.12.12, as shown on the diagram, that is being advertised from 10.99.99.12, which is the IP address of that router 12 here. And we're seeing the autonomous system of that AS as well. And so this is kind of modeling what it would look like if you were a member and you were connected up to the LINX Route servers. You would see the routes advertised by the other members of that internet exchange that are peering with the route server. You would see the routes as coming from them, not from the route server. The route server does not insert itself in the route, and you don't see the autonomous system either, that the router or the route server in the internet exchange is using. If we take a look at our configuration again, just to be the configuration on router 11, just to wrap up and finish here, we can see how this router has been configured. We saw that it has a session with the root server, and we saw that the root server is advertising it with, 7 routes. So router 11 is getting 7 routes. Those are the routes from the other 7 autonomous systems. We can go down here and verify to see how this router has been configured. So this is the line that sets up the router to go and talk, start running BGP on it. It has a single neighbor statement here, which is the root server and its IP address, 10.99.99.120, with remote AS 250. And the network that this router is advertising is just that network here, 11.11.11.11. And all the other routers are similarly advertising something similar, and those routes are then getting distributed out to the other routers via the root server. Okay, so in conclusion, for this first part of the presentation, what root servers are giving us is the simplification of only having one root server or one BGP router to peer with when you are a member of the Internet Exchange. It is not inserting itself into the data path, so it is not being a bottleneck. In fact, the only packets that are going to the root server are those BGP packets like the keep alives, the routing updates, any other sort of notification messages within the BGP protocol, but it's very low level traffic. The Internet Exchange is going to have, for redundancy, multiple root servers for you to connect to so that you can receive those routes of the other members should one of the root servers fail, for example. What you don't see here is that the actual connectivity of the root servers to that infrastructure is extremely redundant across multiple sites as well. So you've got a very very incident tolerant infrastructure to provide very high availability of route advertisement to enable you to maintain your knowledge about routes to different destinations across the internet. And finally, what it's providing you with is within the infrastructure of the Internet Exchange, a local interconnect point to, hundreds or even potentially thousands of other organizations so that you can directly communicate with them and the networks that they are advertising to you in, again, I would stress, a very highly redundant fashion. Okay, so, well, really, that's all I had for the first part of this presentation. So we are going to take a break now for 10 minutes or so, and you'll be notified when we're about to start the next part of our session. Again, if you do have any questions, please put them into the Q&A, and we'll attempt to address those questions before we start the second half of this session. Thank you very much. I hope to see you in the next half. Okay, and welcome back. It's 5 minutes past the hour. We're going to continue with the second part of this webinar. Katrina, do let me know if you can't hear me. Otherwise, I'll assume that everything is okay on the communication front. Thank you. So we've looked at, in brief, at the overall purpose of route servers. We've seen the way that LINX uses route servers at its Internet Exchange points. We've taken a look at the number of route servers they have here, and we've seen some example of the number of customers they have, or members as they're called, that peer with them to take advantage of this multi-lateral public peering capability to allow many organizations to directly communicate their routes to each other, but with a greatly simplified configuration and then operational environment as a result. Now, what I'm going to do in this second part is to take a look at more specifically at things like the configuration of the route servers. We've seen configuration of the member routers, but we haven't seen configuration of the route server itself. Also to describe the architecture of how the route server operates, and my example is with the Bird Internet Daemon distribution, as I said before, and also to look at things like how we can do some filtering between our members. So, for example, what the route server and what LINX provides is the ability to declare that if there are certain peers that you don't want to advertise routes to, then there are ways in which that can be achieved. So there are multiple different ways of doing that. We're going to look at the use of communities, which is an aspect of BGP. So it's another aspect of the BGP protocol we talked about earlier, and how, for example, those are implemented. And my demonstration will be along the lines of what they're doing at LINX in that respect too. So first of all, then, we're going to look at the Bird Internet Daemon as an example. So more closer inspection of this particular variety of route server. So Bird is, as I mentioned before, distributed under generic public license. It was originally, back in the day, a university project from a student at the Charles University in Prague. It supports both IP version 4 and IP version 6. My demonstration is just trying to keep things simple, so I've just chosen I've just chosen one of those, IP version 4 in this case. Bird is an internet routing daemon supported by Linux distributions, and it not only uses or performs BGP, as is the context of this conversation, but it also supports other routing protocols, including RIP version 2 and OSPF version 2 and 3 as well. Within the routing daemon of Bird, it exchanges the routes amongst these different routing protocols if you are running those different routing protocols, and it does so internally. So, for example, you could use it to run routing for various different protocols, both IGPs, which are what we mentioned before, which are what these are, and the BGP, EGP, and it functions to be able to provide route distribution amongst those routing protocols. But we're not using that here. We're just focusing on the BGP side of things, just a single routing protocol. The way that Bird is configured is that it uses a configuration file which you can edit. There is a default configuration file that is created when you install Bird, and when you run it, it will run from that default configuration file. You can create your own configuration files. You can edit the default one, and you can switch between different configuration files as you operate in different fashions with Bird. And it is a dual stack. It supports, of course, my slide is incorrect. Sorry, that should say IP version 4 and IP version 6. That's that's not what dual stack means here. Please bear with me. I had a typo error here. It runs dual stack, which is IP version 4 and IP version 6. And as such, it can it is going to run it's going to run two different processes to do both of those. I'm just going to edit this here. That should say IP version 4 and IP version 6. So a live edit there. Bird has a command line interface, and you connect to the command line interface by what we call a control socket, and I'll be pointing that out to you. So in our situation here, we're just running the IP version 4 of Bird, or we were just looking at the IP version 4 of Bird, just to keep things simple. It runs on a number of different Linux distributions from kernel version 2 upwards. As with the London Internet Exchange, my example here is on Ubuntu Linux. I'm using Ubuntu 20 in my particular environment. Okay, so I'll give you some more information on that configuration file and that control socket as we go through here. So the configuration file is something by default called bird.conf. It is created for you as the default configuration in this path on your Linux machine. You can start Bird by using a command like this, bird C, to select the configuration file, and then select the configuration file you want if you're not using the default that's here. If there is a problem with this configuration file, then the Bird routing daemon will actually fail to start. And if you are running it for the first time and you haven't used it, then there is a command which I'll put on the slide here, which is bird -p, and it will scan the we'll scan this configuration file and tell you what lines and what characters in the lines it finds some inconsistency in the syntax. So if you've got any syntax consistency, for example, in the configuration file, or you put something in which it doesn't understand, or you put parameters in which are not acceptable, then a bird won't start. But if you use this command, it'll tell you what errors you have, what conflicts it's found. Secondly, there is a control socket, which is what I've tried to illustrate on here. This is where I've talked about it in run bird.ctl or bird6.ctl. There is this control socket. The control socket is created when bird runs, and your command line effectively is connecting to that control socket to use the command line. And we'll take a look at that command line in just a little while. You'll see how that is working. If you want to see the bird process that's running, we can see that the bird 6 is running in the background. This is the one that I had started when I used this command here. And you can see it's the bird.conf that gets selected when I started bird using the command that I'm showing you here. Okay, so you need a configuration. Sorry,
we have got a question. I don't know if it's a
oh, I
good
didn't
time to
spot
ask.
that. Hello, sir. I
Sorry.
joined late, so I just wanted to know what bird is. Oh, I'm sorry. Yes, sorry. Somebody just joined. They asked what bird is. So, bird is an internet daemon. It's an internet routing daemon. It runs on Linux, and it's being used as the daemon that's running the routing protocol on our root server in the illustrations that I mentioned earlier. So thank you for the question. Just a little bit of clarification there. So we're taking a look at bird in more detail here. We've talked about, in general terms, about root servers earlier and how they function. Now we're looking at more details of the particular implementation of a root server with respect to bird. In general, then, and this will help us to understand when we talk about filtering later on. In general, the way that bird is operating is that it has a central routing table where the routes that it's going to use, just like any other router for routing packets, is a construct that we have over here. When this router connects by interfaces to other routers, then it's exchanging routes and it's learning routes with other routers over here. And so I just put three instances here of three routing protocols or three sessions in the context of BGP. Then every router that is connected or has a session, as we illustrated earlier, with the root server here, is going to have one of these instances of BGPs running. So in other words, there's a routing protocol instance for every BGP peer that the bird routing internet daemon has. The routes use a preference value to add a sort of metric and a sort of weight to routes, and those routes that are learned from peers go through an import process, and we'll see this in the configuration file, to get into the routing table. And if we didn't want them to be in bird's routing table at all, then we would have some policy in the filtering layer here between the external peers and bird's routing table. Now, if we want to accept routes from peers, but then filter routes on the way out from bird, then we'll use the export filtering You can see this listed on the side here. So we have basically an import and an export filtering layer between the peers that we are, in our case, BGP peering with, and we'll run an instance of BGP with every or a session with BGP with every peer that we are pairing with in this routing daemon. With no filters, then what we receive will come into our routing table, and if we're acting as a route server, as we are in this case, those routes will be shared with every other peer. Okay, that's the context of how that configuration layer can influence the way we connect to and how we can announce our routes to the peers that we're connecting to. So in order to connect to the command line, we use birdc, and it'll give us a quick status. It'll tell us what's running, and the prompt will change to a greater than sign and showing bird before the greater than sign here. So birdc effectively connects us to our command line. We can reconfigure bird to use a particular configuration file from here, and we can do things like confirm our confirm the status of the configuration to see if anything needs to be done. So once we're in bird, we can actually switch between configuration files if we have multiple options, and it will reload the configuration file that we choose. We can also do things like undo, for example, if we go to a configuration and we want to undo and go back to the previous configuration. That's what the undo function is using here. Bird remembers the last configuration we loaded. So if we go into the bird configuration line and we use just the line configure here, it's going to go to the last configuration file that it used to load. And if there are any changes in there, it'll tell you about any changes. So for example, if you made some changes to this configuration file, it'll tell you that it's now reconfigured and it's up to date with the changes that you made in that file. So it's very versatile, and we can swap very easily between these different files. So if I just jump over to my environment very quickly here and pull up this this Linux machine window here, for example, I can see that we're in bird. I can type configure, and it says I'm reconfiguring here, and it puts me back into the prompt, and it's using the configuration file. I'll just put my cursor at the line where it says reading configuration file, etc. bird.conf. That's the file that I've asked it to use. If we go and just take a look at what that configuration file looks like, I'll show you it on the slide here because I've got some annotation to point things out to you. Then we'll go and take a look at that file actually on the machine that I have. So you'll find in the default configuration file, there's a whole bunch of annotation. The hash is used for annotation. And just as a general point, you know, every character is a space, or white space is a space in the text here. When we set up the root server, we have various different things. We have variables for different constructs, and we've had parameters. For example, this one here, the router ID. This is the address by which this router is known, or it's an ID by which this router is known, and it's given an address structure. Each of these parameters has to have colon at the end. Sometimes when you're making variable definitions, you can define your own variables. So for example, down here, using the define string, we can define these peers and what ASs they're on. So this is going back to my lab environment. I define peers as peer underscore 1 AS to 8, and these are the AS numbers that they have been defined with. So define is a key word in this language. Now we have in side of Bird this kernel protocol, which is always running. And this is responsible for the import-export policy of the kernel amongst the different routing protocols that I mentioned before. So if you're running RIP and OSPF and BGP, then you can redistribute between them using this kernel here. We're not using that here, so I've edited out the export function, and I put none for importing. And there's a default timer that is used to scan that protocol interface. There is also another protocol here, which is the device, or and what this is basically a control interface that scans the interfaces in the machine where you have Bird running. The scan time is the scan time used by Bird to scan the interfaces on your machine to make sure that it has the most up-to-date information. But really that time is not so relevant because and we make it 60, which is 60 seconds, which is quite high, because Linux itself will announce to Bird internally if there are any issues with any of the interfaces anyway. So Bird will be updated via the Linux kernel running on the machine. And then we can dump our logging to a file called syslog with this command that's down here. I want to show you as well with the annotation before we actually go to see Bird live that we can, or what we need to do is we need to set up some parameters in order to create the peering sessions in the same way that we create peering sessions with the Cisco iOS on the Cisco routers. With Bird, we need to create sessions between Bird and those Cisco routers as well. So individually, there is a BGP protocol session running with all those peers that we individually defined. And I've given the remote AS number and the neighbor number for each of those 8 routers numbered 11 to 18, and ASs, which are 1 to 8. Okay, that's what I've called those ASs here. I'll call them peer 1. And remember in the definitions slide and the definitions on the previous slide, their AS numbers for the peers were 11 to 18. So it takes those values and substitutes them into those peering sessions. And then on the root server itself, I create a template for it on the root server to then have a session with each of those peers. So I create an object up here called root server clients, which is a template in BGP, and then that value there gets substituted for the root server clients that I individually defined down here. So for all of those remote peers, the root server has these parameters: the IP address of the root server, which is the interface on the Linux machine that this root server is running on, and it's AS250. And then the policies within Bird to do root distribution amongst, in this case, the different peers that I have configured here. So by default, I'm importing all and I'm exporting all between the 8 different peers that I'm talking to. You can put on here things like import limit. So this is import limit 10,000. So, for example, if you are a root server in Exchange and you have, something like, I think the LINX Route Servers had something like 300,000 routes being advertised through them. Um, I could put a limit on here of, like 350,000. So if there's a massive spike above that, something wrong in the internet, then I can be warned of it and I can drop those additional connections beyond the normal limit. When I am setting up Bird as a root server, I must put this line in here, RS client. And that makes this Bird distribution a root server for each of these clients or each of these peers which it's pairing with. And you can do things like graceful restart to make sure that, if the other end does boot, then you can keep a copy of the routes that you already have for that peer, rather than immediately flushing them out of your table to get a BGP smooth transition if something should happen on the network. So that's the overall general way that the configuration looks. I'm just going to go over here. I'm just going to exit out of this prompt for the moment. Sorry, excuse me. If I type here, and then I type to take a look at the bird config file over here quickly in real time. Whoops, I think I have just typed something incorrect there. So what did I type there? Sudo, etc. Excuse me, I didn't put in the full path. That should say bird. Oops, not doing very well here, am I? It's always the way when you do things live. That looks a little bit better. So there's my configuration file. This is my adaptation using those things that we saw on the slide. I go all the way up to the top. And you can see it's all in there as we just described. We've got the kernel here. We've got the router ID at the top. We've got the peers defined here, the logging, the template for the root server to talk to all the other peers, and then those defined peers in there. So this configuration doesn't have any filtering in there. It is just as you see here, like so. Excuse me. We can go back to the bird command line from there now as well. So that's the configuration. Let's move on here. In terms of operation and monitoring, we've seen the command just now to get into the command line and the prompts that change. Within the environment, you can see some idea of what this root server is capable of with in terms of show commands. So we can see interfaces, we can see routes, we can see overall status to see how things are running. So we can see how things look from the point of view of the root server. So for example, show status will tell us what version we're using, what the router ID is that we've configured in the config file, what the current time is, the last boot time, and the status of the daemon. So Again, if I just dash across here and show you. So that's the information that we can see that's in there. We've looked at the configuration before that allows you to choose between different configurations. And if it's up to date, you can use this configure confirm command that says, whether there's any changes that you've made to the configuration or not. So while it's live, you can modify the configuration file and then use the command configure, and it will reconfigure the changes that you make sort of on the fly. Now, if we want to see how things are looking from the architectural point of view, its interfaces, and the routes that the routing daemon is using, then let's go and do that. You can see that those two commands are there on the slide, but I'm going to jump over to my environment here. So you can see that the Ethernet interface with the address 10.99.99.120 is the one that we're using to peer with the other routers. And in fact, that's also the address that I'm using as the router ID in my routing daemon. There's also a loopback interface for testing, and there's the Linux Docker interface here, Docker 0, which, if it was configured, can provide, for example, if you were using containers with BGP running on them, then through that, Docker 0 is a bridging interface that will allow you to interconnect amongst containers or between the containers and the Linux system itself, where you're running Bird, and you can share routes through that Docker 0 bridging interface that's there. The command show route was the other one. And so it's going to give us, as we can see here, we've got routes 11, 11, 11, 11 to 18, 18, 18, 18. It is a loopback interface. That's why it's got a /32 on there. And you can see that there are a number of different aspects with a via field and the peer that's advertising, and some BGP path attributes associated with those as well. Let me just jump back to the slide here and point out what those are. So when you peer with BGP, you will see you'll see your route, but you'll also see the what we call path attributes of the route in the device that's peering with you. So that's what we were looking at then, and I'll explain that to you in just a second. There's also this command here, show protocols, and what that shows is that it shows the kernel and the device protocols that were part of that default config. We explained those, and it shows you that each BGP peer is running a separate instance here, or a separate protocol instance, and Bird by default is what it learns on one BGP instance with one peer is then announcing those routes to the other peers. And those routes, or those BGP peer relationships, are all in what we call an established state. And if they weren't established, we wouldn't be able to learn routes or share routes with those, with whatever individual peer was not in an established state with the route server. So the show route that I was mentioning and we saw just now on the actual device, so we see that the route is here and the via field is where that is coming from. So in other words, that's the address of the actual peer that's advertising those routes, as we had in our diagram. There's a peer name when it was set up. There is an asterisk, which indicates that that is an active route. That's what the asterisk means here. The 100 is something called local preference, so that if the route server advertises that route in IBGP, it will use this as a local metric. And then we see the autonomous system number of the advertiser of the route that's of the peer that's advertising that route, which is 14. And the I means that that is what we call an IGP route. It's a route that was specifically added to BGP by the peer that's announcing it to the route server. And you can see the breakout of all those components in here per line with the show route all command. You also see a little bit more. There's another BGP metric called MED here, which is also added in there as well with that command. So it's the routing table. You're seeing the routing table of the route server and with all the various BGP metrics that go along with those routes. And these are the routes then that are received from the individual peers, and they're then sent back out to the other peers that the route server has. So the route server will receive a route from a peer and it'll advertise it to all the other peers, but it won't announce that same route back, obviously, to the origin of that route. And we can go and have a look here and do the same thing. Show route all, and we can see all those routes in here as well, exactly the same way that we just saw in the slide there. We can also turn on debugging. Okay, when we turn on debugging, we need to echo that to the command line, and those keep alives that we saw earlier when we were looking at Wireshark. We can quickly go and have a look at those again here. So there were all the keep alives between the different peers. They're still running. And we can also see those through the debugging in Bird, and we can see where those keep alives are coming from, as in the, got a keep alive from peer 8 here, and who we're sending as a route server peer keep alives to keep those BGP sessions open. We can also debug to a specific peer by putting the string name of the peer that we've defined in inverted commas. So this command here means debug the BGP from this peer here, or debug the routing protocol from this peer here, and we want to see everything, including BGP. We have to put it in quotes, and you can see that that runs there. We want to turn off debugging. We just turn off debugging with debug all off. So I'm going to jump over to my environment here and say debug all off, and then that will turn that off here. So it's very good to be able to see that the sessions are alive. We don't have to go into Wireshark. I've got the luxury of that here, but we can see through the debugging what those sessions look like and which peers are up and running. There's a slide just to show you again the debugging. In this case, we can see routes from a given peer. I'm going to run this one because I'm going to show you a little bit of filtering in a second, so we can take a look at this. So if I want to, for example, see the routes from a given peer, so any changes in routes, then I can use this command syntax here. And if that peer then announces to me different routes, then I can see those specifically through my debug, my debug here. And my peer is called 1. And I need to put that in to curly brackets like that. And so I'll be able to see if there's any changes in my relationship with that peer via that command there. So we can configure various different configurations and different profiles. We've seen how those configurations are used in a configuration file, and each peer that we are talking to has a different instance, peering instance in the BGP protocol, and by default, the root server is going to share those routes with each of the peers that it is pairing with. So in my case, a route comes in from one of those routers and it is shared with each of the other routers that it's pairing with. And if we want that behavior to be changed, so it's very often the case, for example, that you as an organization may want to go into some sort of maintenance, for example, and not have your routes advertised out for a period of time, or you want to be selective with whom you want to advertise your routes when you're in this public peering forum. So you want to be using multilateral public peering. You want to be using the root server in the Internet Exchange to get the ability to advertise very simply to all of those peers. But there may be some peers that you don't want your routes to be advertised to. And so there is a mechanism within BGP that allows us to tag routes so that we can control how those routes are being advertised when we're peering with other routers. And that is what we're going to look at here in the instance of where we want to be selective, or we want to, or we want to have the routes that we're using just not be advertised potentially to anyone. So I've got two fundamental examples here to illustrate what I mean here by filtering. So the first one is where we're using what we call well-known BGP communities. So well-known BGP communities are community strings that are used with our routing updates and are generally understood by all BGP routers. Some you have to configure to apply a policy that is going to adopt what you're trying to signal to them using communities, and some just understand the well-known communities fundamentally from the start. Bird understands well-known communities fundamentally from the start. So we'll have a look at this in just a second, but for example, what we're going to look at is that if you, for example, are AS11 here, this is your route. But if you want to advertise that route with the well-known community of no export, then what you're saying to the root server over here is don't send this out to anyone. Okay, don't export it. It means that this BGP router can't send that route out of its autonomous system. And in our case, we're using Bird as a root server in Autonomous System 250. If we send that route to Bird, but with the no export on there, it means we don't want Bird to advertise that route to anybody at all. And of course, that's one thing, and we'll see that's a very simple setup. Additionally, what Bird has is a very simple programming language using ifs, else, and then, but without the use of loops. So we have to have kind of nested if and else. And I'll show you the setup that I have for a particular example. So what this allows us to do is to be selective. So if the autonomous system here wants to send a route out, but it doesn't want that route to be seen by a particular peer of the route server, then we can use this programming language here within our configuration file to tell the route server that we don't want this route to be sent out. So a BGP community, as we'll see when we look at the packet in just a second, is what we call a path attribute that is added to a route advertisement and is meant to signal to the peer router we're peering with some information about the route. And in this case, we've got two examples. One is to say, don't send this route to anyone. That's the well-known community of no export. And in the second instance, we're going to say, don't send this route to that particular peer. And that indeed is how the filtering is performed if you're using the Bird route server to do filtering for you. So on the router 11, which is the router I'm using to do this demonstration and send the community with a routing update, I need to configure it to send the community, the first instant, to send the community of no export. So what I do is when I'm telling it to go and talk to the route server, I put an additional string here, which is send community. That needs to be there. And then I have a mechanism called a route map, which is called set community down here. And that will apply conditions to the routes being advertised to this device in the outward direction. And the route map here is specified. So this is like my preferences that I want to apply to my advertised routes. I have a route map called set community, and I have a sequence number or index number here, and I say set community to no export. Okay, and then I send my routes to my peer, in this case, the route server, and those routes will be sent with the no export string in them. Okay, I have a slide here to show you what this looks like in the capture, but we'll go and do this live. So when I capture now my outgoing packets to my route server, I'm looking for an update packet, and this particular update packet here is sending the routing update with this community that's in there. So let's go and have a look and see if we can implement that. So currently, if I go and take a look at, say, router 12 here and do a show IP BGP, we can see it's got all routes, including the route from number 11, which it received via the route server. If I go over to my router 11 here, I'm just going to modify the configuration now to send out that no export, the no export configuration. So just bear with me a second while I put this configuration in. You'll see me put that configuration in here as a quick demonstration. So I'm referring to that set community route map here, and I'm saying on that set community to no export. Before I do this, I'm just going to go up here and change where I'm doing the capture. I'm going to go up to this router so I can see the packets coming out from this router. I can quickly inspect the routes being advertised here. Going to filter only on BGP, make that a little bit bigger here, like so. We should see a keep alive popping up there in just a second. I'll go back to this router here, and I'm going to set my community there of no export. And what I'm hoping is within 60 seconds or so, I'm going to see an update. I may have to give it a kick if I don't see this come very quickly. So bear with me just for a couple of minutes. And we should hopefully see a packet go out here with the no export on there. If not, I shall issue a command. There we go. There's my update message. So BGP, unfortunately, has a little bit of a timer thing on it, so it does delay things. If I go and inspect that packet in detail, it's an update packet there. There is the route being advertised 11.11.11. And if I go down here, I can see there's the community being advertised with that route. I should now be able to go to my router 12, do an up arrow again, and this time the route 11 isn't there because I've told that router to issue the no export, and that's told the route server don't send that route out. Okay, so that's what we got. And the route, if we have a look at that route inside of the route server, it has this decimal number assigned to it that looks a little bit like that. There's a bit of a hex to decimal conversion that's gone on in there. Now, in LINX, they have route server policies which allow us to assign a particular filter to routes going out to a particular neighbor. And they have this policy here, which is if you send me a route, not the no export, but 0 colon and then the peer AS, this is the AS you don't want the route to go to, for example, then when you advertise a route to them with this community, then they won't advertise that route to that particular AS. The one we're going to use here in the example is AS number 18. So if you just bear with me a second, I'm going to go back to my lab environment and try and demonstrate this to you quickly as a final demonstration here. First of all, I'm going to just take off the no export, and then I'm going to change that community to be 0 colon 18. And what I want that to do then is now to make that router send another update, which we'll see in just a minute, that will be sent out now with a new community on it, which should hopefully come in very, very soon, within 60 seconds. And we can go and then have a look at the routes being used. But what I'll have to do here is just go in and change the bird to use the new configuration file in order to implement my change. And it's called bird and it's called birdf.conf. Okay, I've now configured my bird with a new configuration file. I hope I've caught this in time. There is a new update from 11 that has come in. And now I see my community as being reserved here. I hope I configured my bird in time. And if I do, what I should see over here is that now the 18 router doesn't see that route, which is the 11.11.11.11 route, because that's being filtered. But the 12 router, if I go back over here and show IBGP, then the 12 router does, because I've told with that route map, which is community 018, I've told Bird, please don't distribute that route to router 18. So this allows users to have control over where these routes are going, who they're being sent to, and these communities can be used then to implement filtering so that you only pass on the routes to who you want to pass the routes on to. So I'll just show you very, very quickly, just as we come up to the hour. There is the way we implement this is in the config file, we use this configuration programming language with ifs and else statements. So for example, here, what I've said is if the source of the route is BGP, that's what this means. And the route is 11.11.11.11, then go to this here. If it's not this route, i.e. it's from another peer, then accept. So all other routes that are not this will be accepted in this case. If it is this route, then check the BGP community string, and if it's 018, then reject it, don't allow it through. If it's not that community, then you can also allow that through. So for example, if the sender of this route took off that community, then it would be sent through perfectly well as well. So there's a little bit of a rush at the end there, but and I won't have time to talk about this, unfortunately, but I would just like to finish and conclude my session here and say that LINX Route Servers are used in multilateral peering. It makes peering with other ISPs simpler by using a single agreement or BGP sessions. LINX Route Servers are not in the data plane and therefore do not slow down traffic flows at all. The local interconnection, therefore, of hundreds of ISPs and cloud content providers gives you high performance, great connectivity with lots of redundancies in your connections, and the use of communities enables you to control exactly how you as an ISP, as you as a member, want to distribute your routes to the other peers. Thank you very much. I'm sorry there's a little bit of a rush at the end there. I hope I still managed to convey what it was that I was talking about. I hope you found that session useful. Thank you for joining, and I hope to see you on another session in the future. Many thanks.